Hello and welcome back to the final video in our adiabatic flame series. Today we're going to be wrapping up our Python simulation of our adiabatic flame. We left off right here after having run all of these as I talk. We left off last time doing the properties, getting that from our ChemTools package that Carlos has written for us. We developed our own formula to calculate the enthalpy of all of the substances we'll be using in this reaction for any temperature, which includes the heat of formation as well as the heat capacity integrated over the temperature of standard state, 298.15 Kelvin, to whatever temperature we are currently at that we're going to be looking for as we do this problem solving. And then we compared that, what we get just right here is our test case of 300 degrees Kelvin, or 300 Kelvin, and you can see that they match. So that's really good. So anyway, we're going to get rid of these. So I'll clear these out of the way. And we can start on with the next part. So what are we going to do next? Well, you remember in our first and second videos on the chalkboard, we talked about the stoichiometry and how we could, first of all, describe the stoichiometry and then generalize it for hydrocarbons of any size being combusted. So how do we do that in Python in a way that allows us as much flexibility as possible to change and adjust things as we need? So what we're going to start off with first is describing the fuel composition by mole percentages. So we're going to make, first we're going to make a variable called fuel comp right here, and it's going to be equal, it's going to be an NP array right there, and it's going to be, and I believe you put an actual array in. So it's the NP array function takes an actual array and classifies it as an NP array type using NPs, numpys, fancy mumbo jumbo Python code. So what are we actually working with here? Well, we remember our fuel composition is 95% methane, 10%, no, yeah, 90% methane. I automatically just did the 10% left. No, wait, let's see a second. 95%. 95% methane, 4% ethane, and 1% propane. So we're just going to plug those numbers in here, 0.95, 0.4, and 0.1. And outside, I'm just going to say meth, eth, and prop. So this is our fuel composition, 95% methane, 4% ethane, and 1% propane. So what do we do now that we have this? Well, what's important, remember, for our stoichiometry, when we started it and tried to generalize it, we realized the first most important things are the number of carbons and hydrogens in our hydrocarbon, because from there we know the amount of H2O and CO2 we have to produce to balance that, and then from there we finally wrap it up with the oxygen and then the associated nitrogen that comes along in the air we combust. So we're going to do the same thing, but we're going to do it in a really, really nice way using arrays and matrix multiplication. So we're going to start by making a variable called fuel ch, and this is also going to be an NP array. So we're going to make an NP array, and this NP array is going to contain the number of carbons and hydrogens in each one of our fuel molecules. So this is going to be an array of arrays. So I'm going to give this a bit of space in here just so we can visualize it. So the first entry in our array is going to be an array to describe methane. So methane is 1 carbon, 4 hydrogens. I don't think we need to do these can be left as integers. We don't have to put the point values in. So that's our first value. The second value will correspond to ethane. So we're going to need another array that's going to be 2 and 6. And finally, our third array that describes propane is going to be 3 and 8. So we have an array. It's a 2-dimensional array because it's an array of 1-dimensional arrays. So this, if you notice, has 1, 4, 2, 6, 3, 8. That describes the atomic composition in carbons and hydrogens of, methane, ethane, and propane. So how can we use this array of the magnitude of carbons and hydrogens and the percentage of fuel to pump something out that's actually useful? Well, that's where matrix multiplication comes in. If we think about the matrices, this being a 1 tall, 3 wide, and this being, if we stack it up like this, and give a backspace there, you can see that these together can actually do matrix multiplication down the rows. Again, multiplying 0.95, 0.4, and 0.1 times 1, 2, and 3, and 0.95, 0.4, 0.1 by 4, 6, and 8. And if you were to do that matrix multiplication, what you'd actually find is that that will take the average amount of carbon and hydrogens between all three of these substances, taking into account their availability, their proportional existence in our fuel mixture that we're burning in our Bunsen burner. So how can we do that? Well, that's just simply linear algebra. What we're going to do is we're going to multiply our, I think fuel comp comes first because it's length times width, because it has to be a 1 by 3 times a 3 by 1. So yeah, fuel comp has to go first. So we're going to multiply fuel comp, and we're not using regular multiplication because that's not what we want to do. We want to use matrix multiplication, which is the @ sign. That is the Python code for matrix multiplication. So the fuel comp multiplied by fuel, make sure I spell fuel right, fuel CH, there it is. And what do we want that to be? Well, as I discussed earlier, it will start left to right. So the first thing we're going to want is going to be the 1, 2, 3, which describes our carbons. We're going to call this NC for moles of carbon, and we're going to have the other one be hydrogen. So we're going to do NH for moles of hydrogen, and that's going to be equal to this matrix multiplication. So now that we've done that, we actually have the number of moles of carbon and hydrogen that are in this fuel mixture on average. So now that we have those average values, we can calculate the average amount of CO2 and H2O we're going to be generating from this, kind of based on what we did on the chalkboard. I'm just going to be doing it shorthand and talking as we do it because we've already kind of thought this out ahead of time in our chalkboard video. So the moles of CO2, I always hold shift and then hit 0 instead of shift and O whenever I try to write CO2, or just usually capital O's in general. I'm probably going to do the same thing with oxygen, but don't worry about it. So the number of moles of CO2, as we discussed in our chalkboard video, I believe it was chalkboard video number 2, but it could be chalkboard video number 1. Not super clear in my head right now. But what I do remember for sure is that it is going to be a 1-to-1 ratio, because CO2 has 1 carbon, and all of the carbons are going from our carbohydrate into our carbon. So that's just going to be equal. They're going to be equal to each other. Next up, the easy one is going to be H2O. We know that the moles of H2O are going to be equal to, well, we said that every single hydrogen in H2O comes from our hydrocarbon. So we know that since water takes 2 hydrogens, H2O, it's going to be the moles of hydrogen divided by 2. So that one's pretty easy. We're going to add a decimal point there just because the moles of hydrogen is going to be some decimal, obviously, depending on if we changed those fuel composition percentages, that would also change as well, but we're not worrying about that because for this case, we're only looking at that 95-4-1% mix. So what comes next is oxygen. Now, oxygen's a bit more complicated, especially because of the extra interesting thing we're looking at, which is imagining pumping in an extra 20% excess air from what our reaction actually requires. Because again, all of this math is basically taking those 3 combustion reactions we did prior, or all 3 of them, and then the generalized case, and doing a per mole reaction. So we're imagining that 95% of the reactions are single carbon, dual carbon, and then triple carbon. So now that we do oxygen, we do NO2. We're going to set that equal to. So we remember that since carbon dioxide has 2 oxygens and H2O has 1 oxygen, if we double the moles of CO2, that will tell us the moles of oxygen. So 2 times NCO2 plus, we just add the moles of hydrogen because each moles of water, because each mole of water has 1 mole of oxygen in it. That would be just plus NH2O. That will give us our total moles of oxygen. However, we do have to remember that both of these have to be divided by 2 because our oxygen comes in packets of 2. Oxygen's standard state is O2, so of course we'll have to divide this whole thing by 2. However, because what we're going to be doing in a quick second, it's actually easier to just, instead of wrapping this in parentheses and dividing it by 2 there, it's easier to just do the division by 2 right now. So 2 times the number of CO2 divided by 2 is just the number of moles of CO2. We do the division here, like so. So now we can wrap this guy up in parentheses and call it good. And we'll see why we're wrapping it up in a second, but let's just continue on to nitrogen really quickly. The moles of nitrogen are fairly simple. Moles of N2, well, that's just going to be equal to however many moles of oxygen we have. So that's NO2 times that special multiplier to describe the air saturation of the two elements. Again, we're assuming that nitrogen and oxygen are the only two elements in the air we're breathing and feeding into our Bunsen burner as an oxidizer, and that ratio is 79% nitrogen and 21% oxygen. Those two add up to 100%, obviously. We're going to add some decimals in here and here and here just to make sure nothing is forced to be an integer, and hopefully that will cover everything. So now we have the number of moles of every single one of our elements right here that are going in and out of our combustion. And now all we have to do is figure out how to factor in that excess air. So how exactly do we do that? I'll add some little space up here. How do we figure excess air? So what we're going to do is we're going to make a new variable. We're going to call it, well, for lack of an imaginative term, we're going to call it excess underscore air, because why many word when few words do trick. So excess air, well, in this case, we're talking about 20% extra air. So we're going to do 0.2 because that's the easiest way to put it. So now how can we figure this in? Well, we know that right here, these two both purely depend on the hydrocarbon that we're burning. So we're not going to bring it in here. And we know that whatever that excess factor is, as we discussed in our chalkboard videos, is going to affect both our nitrogen and our oxygen. So the easiest way to implement it, since we're already determining our nitrogen based off our moles of oxygen, if we incorporate it into our moles of oxygen, that extra factor will automatically be carried in right into our nitrogen. So if we implement it somewhere here, it'll be fairly easy to figure out. So if we want 20% excess air, that's equivalent to 120% of what our original air moles would be. So the easiest way to implement that would be to multiply whatever our original moles of oxygen are by 1 plus this 0.2 factor to bring it up to 120%. Because if our excess air was 0, we'd be adding it to 1. If I type this excess air, we'd be adding 0 to 1, and multiplying something by 1 obviously just gives you the same number. So now with this excess 1 plus this 0.2, which is the excess air variable, we're incorporating 1.2 times as much oxygen gas as we need, which then factors that extra 1.2 multiplied obviously by the commutative power of multiplication, or whatever says that you can just keep multiplying things together and it doesn't matter their order. That makes its way into the nitrogen as well. So with this, it worked. Hopefully it's all correct. We can actually check. Well, yeah, we'll check right now. What is the average amount in moles of nitrogen? So NH. What is NH? 7. I'm going to assume that checks out. Because, I mean, yeah, definitely bigger than 4. And those 8s are going to be heavy, carrying quite a heavy. What about moles of carbon? 2.05. Okay. So those are our two average. So on average, our combustion is using up 2.05 moles of carbon and 7 moles of hydrogen. So that would give us, including the excess air, how many moles of O2? We're using up 4.56 moles of O2 per mole of reaction. Because again, this reaction is averaging the 3 different reactions for each hydrocarbon and just kind of mashing them into one for ease of convenience. So now that we know the actual moles that are being used per reaction, how do we take those and relate that back to the enthalpy calculations we figured out earlier? Well, the easiest way to do it is to just simply mash together all of the inputs and outputs, because we're going to be doing different calculations to both of those. And since we already are given our set right here of all of the properties in this order, and when we plug things into h of t, we'll be returning values in this order, it makes sense if we were to calculate what's going in and what's going out before we actually plug those into our enthalpy formula in this order, obviously getting rid of anything that isn't coming in or isn't coming out respectively. Like, for example, we're not actually feeding water into the combustion reaction, so any calculations we do for figuring out the energy spent bringing things in, we don't want to include water. And vice versa for hopefully assuming that our work, since we are assuming that our reaction is using up 100% of our fuel, we don't want any methane in our calculations going outwards. The only things we want going both in and out are oxygen and nitrogen, these 3 up here being solely in, and these 2 down here being solely out. So how can we do that? Well, the easiest way is to use the NP function concatenate to mush together all of these molar values into a single array. So we're going to do that in a new line by making values called n underscore in and one called n underscore out. So as I said earlier, we're going to be using the concatenate function, so np dot concatenate right there. And when we do that, all we have to do is make an array of what we want to concatenate. So what exactly do we want to concatenate? I'm going to give a little bit of space here. So the first thing we want is actually our fuel composition, because that will tell us, obviously, the amount of hydrogens and carbons that are going in. Get out of the way here. So that's the first thing we're going to put in, because with that, we'll know those ratios that are so important. So we're going to feed that in first, fuel comp right there. And the second thing we want is going to be an array of all of the gases that aren't included in that fuel composition right there. So that's going to be our CO2, our H2O, our NO2, and our N2, because again, this covers all of these guys up here. So we have those three, which are again have already been appended, and then we're also going to need to take all of these things. So we're going to need to concatenate. Excuse me again. We're going to need to have an array of all of these values right here. So concatenating, again, combines arrays together. So these right now are simply float values in their single thing. So in order to concatenate that together with our fuel composition array, we're going to need to actually include we're going to need to combine these into an array together first before actually smushing them together with our fuel comp array. So we're going to need to do another np.array, and that's a parentheses bracket. So now we need an array of everything else. Well, we have to remember the order we put everything in, which is methane, ethane, and propane, which are our fuels, then oxygen, then nitrogen. So we're going to do it in that order. So NO2, then we're going to need NN2, and then after that we have our moles of carbon dioxide and water. And as we talked about, we're not actually bringing any carbon dioxide or water into the reaction. Those are solely outputs. So we're going to have a 0 and a 0. Now that right there should be all of our inputs when you think about it, right? Something with the fuel comp isn't sitting with me correctly. I feel like it's supposed to be. No, because yeah, these are the moles of each of our fluids. I don't know. Something about that wasn't sitting with me. I felt like we needed to use H and C in there, but we're not bringing carbons and hydrogens in by themselves. For every mole of reaction, we're bringing in each of these discrete substances, methane, ethane, and propane. Taking the average carbon and hydrogens per mole of reaction was just so that we could actually figure out the amount of gases down here that we're using. These are the actual. I'm gonna make sure I note this up here because that tripped me up for a second. You could probably tell why when I was saying we needed to use fuel comp that there was a disconnect up here as to why we needed to, and I no matter how much I looked at it, it just wasn't making sense to me. This is the moles of these three substances. So moles of methane, ethane, and propane in 1 mole RXN, or mole reaction. So this is the hydrogen and carbon, which is useful for calculating how much of the other stuff we need to produce and or consume to make this work. But again, the fuel composition is actually what we're doing. Now, NP out is going to be quite similar to what we did previously, except all of the fuel composition is going to be equal to 0, so we don't want to use fuel composition. So it's just going to be a single NP array. So I'm going to copy this, NP array. So what are we actually pulling out? Well, we know that there's absolutely none of the fuel coming in, though the fuel was the first three. So we can check here our fuel comp. So those are our three fuels. Then we need our nitrogen, our oxygen, and our carbon dioxide, and our, what's the word, water. So I don't know what it just did. Anyway, so we'll come back around to our gases because we have to change those a little bit. But up next, we have to just do carbon dioxide. So that's easy. It's NCO2, right? Because carbon dioxide comes first. Yep. And then water is finally last, NH2O. So that concludes the NP array section. However, we have to talk about our N2 and our NO2. Because just like our fuel compositions going in with 0.95, 0.4, and 0.1 moles of methane, ethane, and propane, and that goes to 0 because they're consumed, We also have to remember to put these periods in as well, but that's besides the point, just to prevent any integer funniness. But we also remember that although nitrogen is not consumed, oxygen is consumed, obviously. That's where we're producing the CO2 and H2O. Now we have to remember that if we were burning all of the oxygen, if everything was running exactly as efficiently as possible, this would be zero. However, we have to remember that in fact we are pulling in more oxygen and of course nitrogen, but nitrogen is not interacting in this combustion at all, so it's essentially just being pulled through the entire reaction and not doing anything besides pulling away heat energy. We have to figure out how much oxygen is actually making it out. Now, at first, that would seem like a really complicated problem until you remember we already figured out exactly how much oxygen we need, and then after figuring that out, multiplied it by our excess air factor to bring that extra number in and out. So we have to remember that we already know exactly how much excess we have because that's the excess air factor. So if we grab that 1 plus excess air, which is that factor of multiplication, and we plug that back in, multiply that by our moles of O2, that will give us exactly how many moles of NO2 we were bringing in, and except to be getting larger. However, if we get rid of that extra 1 factor and just multiply it by the volume of excess air, the percentage, the 20%, that would mean we're essentially multiplying that 120% value by 20%, which would bring it back down to 100% the original value. So this right here is essentially grabbing only the amount of air that is considered excess. This is grabbing all of the stuff that was excess that obviously would not be consumed because it's more than what is actually required to combust all of our hydrocarbons. So with these two, I'm just double checking, we bring in our moles of fuel, our moles of input gases and no outputs. Then we have our empty row of fuel. We have just the excess air that wasn't burned up, and our nitrogen gas, which did not react, and then the moles of CO2 and H2O. I believe those are correct, and all of the it seems the syntax was correct because I was worried about concatenate also if it would be a little finicky, but it was not. So finally, when we look at this, now that we have everything kind of set up, we can actually do the root solver equation that we've been waiting on to solve for the temperature. Because again, all of this comes back to the differential equation where because this is an adiabatic flame and it's in steady state, the total amount of heat, the total amount of change of energy of the system must be zero, which means all of the heat released from committing this combustion reaction must be lost again through the heating up of those products that we're releasing. And the products we're releasing are highlighted right here in our N-out variable. So we're going to define an equation that we can plug into our root solver, and we're going to call this combust. Combust. And we're going to import a vector into combust, and that vector is going to be solely the temperature vec. Because again, we remember that the root solver is meant to handle vectors as initial guesses and inputs and outputs. So right there. So we've imported our vector, set it equal to the temperature, and now what do we actually want to do with that? Because we're checking the combustion, and it's going to, obviously, when it root solves it, it's going to plug and chug iteratively and intelligently guess and check until eventually it finds something that is equal to zero. And because of the equation we wrote before, we know what we want to equal to zero is the difference between the enthalpy of what's going in and the enthalpy of what's going out. So how do we do that? Well, we want to return something, obviously, and that's going to be the enthalpy and the difference between them. So what is the difference between the enthalpies? Well, remember, I just caught myself. We have to return a vector because, again, we're pulling in a vector. We have to output a vector as well, and it's going to be a single item vector. And that vector is just going to be the difference between those two enthalpies. So I'll put a big space here and a minus sign to make sure we remember that we want the difference of them. Pardon me again. The changing in the weather temperature has really been messing up my throat, so apologies if this is not the clearest audio you've ever heard. My throat is not the clearest it's ever been, but that's besides the point. So we already have our function that we made in the previous video, h of t, which calculates the enthalpy of all of our properties at their respective temperatures. And now we have to remember that some of them aren't present. For example, if we were to calculate the temperature of everything going in, because I mean the actual answer is going to be what's going out minus what's going in, but that's besides the point. What's going out, we know that there's no fuel, but when we run the the enthalpy equation, it's going to give us the enthalpy at whatever temperature we look at for all of them. So we have to somehow figure out a way to sort out the things we don't want and keep the things we do. And we can remember that by simply multiplying whatever our enthalpy function gives us by the n out variable we made, which again is an array that contains the concentration, or I guess the number of moles of each of our each of our substances per mole of reaction. And remember, our enthalpy right now is returning in energy in joules per mole. So it tells us the amount of energy in every mole of each substance at a certain temperature. So by multiplying it by the concentration, not the concentration, the amount of the substance going in and out by those enthalpy values, we're able to get the total amount of energy in each substance that is present, because multiplying it by a number 0 obviously will bring that one to 0. So we want the stuff going out is enthalpy at the flame's magical temperature that will make all of our equations be true, minus the enthalpy going in at the temperature we know and love, steady state, standard state temperature, 298.15 Kelvin. So we need the moles of what's going out, so n underscore out, multiplied by, so the moles multiplied by the joules per mole, predicted by the function h at the temperature T. So we have our moles multiplied by our moles, our energy per mole of each substance, because again, HT, remember, returns an array of every single one of those. And we're just going to do the same thing, n underscore out, n underscore in, important, times h. And again, it's all going in at room temperature, so instead of T, we're just going to put in 298.15, and that's taken care of. So right now, if you think about what we're calculating, I'll put a little space in here to make some room because we're going to need it in a second. We see that we're multiplying the number of moles we have by the energy per mole of each substance, and the number of moles we have going in by the number of energy per substance, which is basically just the heat of formation, because 298.15 minus 298.15 cancels out all of the heat capacity, because we're assuming, at steady state is equal to zero heat energy in the heat capacity. So why don't we just run this and throw it in the root solver and say we're done? And the reason for that is because right now what we're outputting is an array of two arrays being subtracted. But that's not what we want. What we want is a final float answer, because again, we need to iterate this for a vector that contains one value that's t, and every time we calculate it, it should get closer and closer to the actual value of t. But right now what we're doing is we're multiplying an array by another array, on an individual, on an element-wise basis. It multiplies the first value of n out, which is 0 methane, multiplied by the first value of the enthalpy at some temperature T for methane, and it'll do that for each of them. So we'll have the amount of energy coming from every single substance, but that will just be sitting in an array not doing anything. So what we actually want is to mash all those numbers together to figure out how much energy we're getting from each of our substances added together for the total net amount of energy generated from these reactions running. So what we're going to do is we're going to encapsulate this whole thing right there, because again, this is an array, and we're just going to do an np.sum of it, which is going to take the array we generated right here, again, the amount of energy per substance in an array, so each substance has its own entry in the array, and then we're just going to add them all up together. And we're going to do that for both of these right here. Wrap u in parentheses as well, and do an np.sum. Now the fancy way to do this is to use what's called a dot product, which is exactly what it sounds like. It multiplies them and then adds them up together, but the notation for that is slightly more fancy, and I don't really want to worry about that when I can just visualize it and understand it much better by multiplying them together and summing them up and then subtracting them, because it would be exactly the same thing. It would just be an np dot I think the word is, like literally it's just np dot for dot multiply, and then you would list these with commas and it would just multiply them element wise and then sum them up together. But I prefer using np sum because I'm a classicist. So if we run this, it's just defining our sentence, our function. Make sure again that it's closed. This is properly returning an element. So for example, if we run combust right here with a vector, because again we need to take a vector, and we say 300 degrees Kelvin, it pops out a temperature, an amount of energy of 153. Actually, that's a lot bigger number than I think it would be. 1,537,049 is the amount of energy it's returning. So that's quite a bit of energy. But anyway, so that's not the entire part right here, because what we want to do is we want to figure out for what temperature is this equal to 0. At 300 degrees, obviously it's very far from 0. If we increase the temperature to 500 degrees, we see we're a bit of a smaller negative number, which means we're closer to 0. If we do it to 800, oh, that's not what I wanted to do. I wanted to do 800. I just did it twice, 800. We see we're a little bit closer to 0. So we're going to just, the process of doing that over and over and over again is to use the root function. So we're going to take the root of the equation combust. I wonder if can you do an exclamation mark in the name of a function? No, it doesn't like that. Okay. I was going to say, if I could make it combust with an exclamation mark, I would really like that. I think that would be really fun. Anyway, so we can't. So whatever, moving on. So we take the root, we take our function right there. That's the one we want to iterate. And this is the part where it should tell me what it wants next, which should just be the initial guess value, which in this case, we're going to go with our classic 300. And that's everything. So we're going to run this. And it says the solution converged. And again, the number that we actually want is this value right here. So we remember how root shows up, and we get this value right here. So we're going to do a dot x. And this returns an array right there. So we want the first element in the array, so we do 0. And we run it, and we get a temperature of 2,082 degrees. So at the temperature 2,082 degrees, we are getting a flame in which our steady state is, existing. And the steady state at which the amount of energy coming in and being created by combustion is equaling the amount of energy that's flowing out as we what's the word? As the flame generates heat and heats up all the gases that are flowing out of the system. It just it reaches an equilibrium where the amount of heat going out and the amount of energy coming in through combustion are equal to each other. So I'm pretty sure that's pretty darn close to the right answer. I remember the right answer being around 2060-ish, and we got 2082. So I'm just going to quickly scan over everything to make sure I got it all right. I mean, I feel like if there were a major mistake around here, it would have been, first of all, hugely noticeable. Is it possible I put a 298.15 and wrote it down wrong somewhere? Let's double check. 298.5, 298.5, 298.5. L times HT, N times 9.5, 79/21. That's definitely the correct ratio. Multiply oxygen, hydrogen +2. I'm really confident on this. I feel like there was something messed up in here. It would have been super simple, right? Because D, C, and C times D, E, and E. I didn't mess that up. Divided by hyperbolic tangent, multiplied by hyperbolic tangent, all things divided by 1,000, because it's closed correctly. Positive, negative. Multiplied by T. Yeah, I can't figure out exactly what's going on here. Oh, I found it. Okay. So, very silly. So these are supposed to be, the fuel composition is 95%, 4%, and 1%. Well, the way it's written right now, it's 95%, 40%, and 1%. I forgot a 0 right here for both of these guys. Let's rerun you, rerun you, rerun you, and now rerun you. And there we go. There's our 2063.86. I was a little curious because I was very close. So the mistake must not have been that major. Apparently, having everything add up to over 100% by over 40%, like a 40% margin of error, not margin of error, but 40% error in these two supposed to be trace molecules was bringing the temperature up, which is pretty interesting when you think about it. The temperature was actually higher when we had molecules with a higher number of hydrogen-carbon bonds, which I guess makes sense when you think that there are more bonds to be broken and therefore more energy to be released per mole of reaction when there are, obviously more bonds to be broken there. But it just goes to show that you should always double check your numbers, especially ones with leading zeros in between a decimal point. But with that, our 2063 number is absolutely perfect, and we're pretty much, we're cooking. We're cooking. We're literally cooking with a Bunsen burner. So we're cooking with gas, specifically a fuel composition of methane, ethane, and propane. So with that, I thank you and wish you a very good night.